Okay. Okay, you can see my slide, okay? Wait.
Yes, doctor.
Yes, doctor.
Okay, wait. Lighting dia. Okay. It's okay. Okay. Okay, we will start class now. So we will begin the last chapter. The last chapter for this course, which is concerning the vector calculus. So this chapter is a bit out of topic from the numerical analysis. Okay, so you will have assignment concerning this topic. He's more into calculus. Okay. Okay, so we see. So in some introduction, I think the first few slides you have. Okay. You have learned this before. Okay, so first part is concerned about the vector differential calculus. Okay, so just revision I think for you. Okay, so you know that a vector, for example A, okay, if you have a vector A which is a function of u, so we write vector A in terms of three direction. For example, if you have 3D, three direction, three axis, so we have AX, the component X, Y, and Z. Okay, this you know. So the derivative of A will be written this way. So the derivative of a vector is dAx over du. So we have to derive each of the component X, Y, and Z. Okay. Okay, next, so this is the nth derivative of vector. We have second order, third order, etc. And then the magnitude of the derivative vector. Okay, to calculate the magnitude, the absolute value of the derivative vector is calculated this way. So we have to square, okay, double the each of the component, okay, and square root all of this. So this one you know. Okay, exercise, actually example, okay, just example. I think, okay, you can try to do this, but this is very, very simple. So you have the position of a moving particle at time t is given by x, y, and z. Okay, function of time t. Okay, a particle is moving at position x, y, and z. Okay, so obtain the velocity and acceleration of the particle. So we know the position, so how to get the velocity? We have to derive, right? The velocity is the derivation of the distance. Okay, so try to do that. Just very simple example. One, just to refresh back your knowledge about the particle derivative vector. Try. I'm trying to write lighting. Okay. Okay, nampak? So, okay. So we write, what was it just now? X 40 plus 3, t square plus 3t, etc. Okay. So if you write vector r, the position r, 40 plus 3, which is the component on the x-axis. So I'll choose, just now we choose ijk, okay, the vector ijk, and then plus t square plus 3t, j plus t power of 3 plus 5t square k. Okay, so the velocity is the derivation of r over p. So we have to derive each component x, y, z. So this one is 4, so for I. The second one, 2t plus 3, j. And last one, the component, the x, the k component, 3t square plus 10t. Okay. Okay, very simple. Okay, just example, just to refresh back. Okay, so the velocity is 4i plus 2t plus 3, the component for j, and for k, 3t square plus 10t, okay? So, and then the acceleration, of course, we have to derive second order, okay? So, second order, I'll just give the answer, will become is power of 2, 2j, this is 0, for I. So 60 plus 10, okay. So this is the acceleration, okay. So and then the magnitude of both velocity and acceleration at t equals to 1. So we have to do the this square root of square of each of the component I, j, and k. Do I have already the answer? I just give the answer, the magnitude. Okay, so for velocity, the magnitude is square root 210. Okay. So for the velocity, this one is square root 210, and acceleration is 2 square root 65. Or you want to write it in decimal also can. Okay, so this is the magnitude of acceleration and velocity of a particle. Okay, I think this is very, very simple. So we move on. Okay, these are some of the rules. Again, just to refresh back. So you have vector A and vector B, function of u. Okay, remember it is a vector, okay, not a scalar. Okay, so this is a vector. So example, if you have a C, a constant, okay, a scalar, a constant. So if you want to derive CA, vector A, so you have to take out C and do the derivation dA over U, okay, because only the vector U is a function, only the vector A is the function of U. C is constant. For example, you have 2A or 10A, something like that. Okay, and then what if we have vector A plus vector B? Okay, so we have to do the derivation of A plus the derivation of B. Okay, and the product, okay, product value, we have to do like the multiplication. Okay, first we write back the vector A and derive the vector B plus the derivation of vector A multiply with vector B. And last one, the rules for, what do we call this?
Cross product, doctor.
Oh, this cross product. Okay, I forgot. Okay, cross product. For the cross product, again, the rules is kind of like this one. Okay, so A cross product of derivation of B plus derivation of A cross product B. Okay, that is the rules. Okay, next, gradient. Okay, gradient of a scalar field. Okay, so we apply gradient. We do the gradient to a scalar field, not a vector. Okay, so if phi, a function phi, function of x, y, and z is a scalar function, okay, of 3 variables x, y, z, and phi is differentiable. Okay, so the gradient of phi is defined as, we can write it this way, gradient, or with this symbol. Okay, so the gradient of phi is the partial derivative of phi in each component. Okay, so for example, if you have phi is 2xyz, okay, so you have to first derive in terms of component x, and then in terms of component y, and then in terms of component z. And okay, so initially phi is a scalar function, but when we add the gradient, when we do the gradient of scalar, the answer will become a vector. Okay, I, j, and k in 3 different directions. Okay, so initially it was a scalar, and then when we do apply the gradient, the answer will become in terms of a vector. Okay, because it has a direction. So example here, also example, okay, we just look at this, okay. So for example, phi, we have phi function of x square y z cube plus xy square z square. So determine gradient phi at point P132. So we have to determine first the gradient, and then we substitute the value of P. Okay, so this the example is the answer is written here. So we have to derive first the function phi in terms of x. Okay, so only in terms of x. When we said only in terms of x, means that we have to imagine that y and z is like constant. Okay, so as if we write back yz exactly as the initial. Okay, so we only derive the phi in terms of x, 2x. The rest we write it back. Okay, so write back y square z square. Okay, we imagine that only the y and z is like a constant, and then the same thing for component y and for component z. Okay, I think we must have known this. Okay, and then okay, so we rewrite all the components that we have, I, j, and k. Okay, that we have derived, and we substitute the at point P 132. X equals to 1, y equals to 3, z equals to 2. So we just substitute in here and we get the solution. 84i, the vector, okay? 84i plus 32j plus 72k. Okay, so the answer is in terms of a vector in I, j, and k direction. Initially, the function is a scalar, okay? With no direction, but the answer, you have direction. Okay, next, exercise 2. Okay, you can do this later on, okay, because we have a lot more slides that is more tougher, okay. So you can try this by yourself later on, okay. So if you have, because the exercise is exactly the same as the example given just now, okay. Just a big change in the function. So you have phi as 3x cubed, yz plus xy square z power of 3. So determine gradient phi and point P. Okay, you can do this by yourself. Okay, next is if A and B are two scalars. Okay, these are some of the rules for gradient. So the rules for gradient tell us that gradient of A plus B. Okay, A and B here is scalars, okay? Just now is vector, right? Okay, this is scalar. Okay, so because we want to apply gradient, okay? So you have to make sure that A and B is a scalar, not a vector. Otherwise, we will not call it as a gradient. It will be called something else, okay? We'll see. Okay, so this one is a gradient of scalar A plus B. So gradient of scalar A plus B is like you do the gradients separately. Gradient A plus gradient B. And then gradient A, B is A, gradient B plus B, gradient A. Okay? So those are the rules. Okay, next. Next function is a divergence. Divergence of a vector field. Okay, so divergence, we apply divergence to a vector. Okay, just now gradient, we apply gradient to a scalar, but divergence we apply it to a vector, but the answer of the divergence will become a scalar. Okay, so it is the opposite. Okay, so we have a vector A, like just now, ax, ay, az. The divergence of A is defined as, we can write divergent like this or like this with dot here. Don't forget about the dot here. Okay. So what does it mean by divergence A? Divergence A is the product of the divergence. This partial derivative of x, y, and z. The product of partial derivative with the vector A. Okay. So it's like we use these rules, okay? These rules, C. Okay, the product rules. It's just that A, the vector A is the vector of the divergence vector, okay, the partial derivative, and B is the vector, okay. Okay, so we do like this, the dot product, okay, so divergence A will become this way, okay, a scalar, plus, 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 so it will not have direction, there's no direction because we imagine that when we multiply, we do the multiplication. For example, okay. For example, we multiply the partial derivative of x with ax. So I multiply with I becomes 1. Okay, the magnitude becomes 1, right? I multiply with I, the same direction will become 1. So that's why we have this component. And then if you multiply this one with AYJ, I and J is orthogonal, perpendicular. So I and J will become 0. So that's why, So that's why we don't have this component, okay, IJ. And then the same for IK and then JI, okay. We only have left with those component with the same direction, I and I, J and J, K and K, so that's why we have this one. Okay, so the answer of the divergence is a scalar, okay. So example here, again, so we have a vector A, this one, so that determine the divergence A at point 1, 2, 3, okay. So very simple. So you just do the partial derivative of component AX, okay, with this component. This is AX, this is AY, and this is AZ, okay. So the first component, we derive it in terms of X, so we imagine this Y is like a constant, so only 2XY, and this one we derive in terms of Y, so copy back negative XZ, okay, and the rest, okay. And then substitute the value 1, 2, 3 inside this. So we have the answer of the divergence A is 13. Okay, I think until now it's very, I hope you get it. Okay, this one, again, I think you can do by yourself also, because it's quite the same. Okay, so you have a vector A, etc., etc. So determine divergence A at point 3, 2, 1. Okay, next, remarks. So this is just some remarks. A is a vector function, but divergence A is a scalar function, like I've mentioned earlier. If divergence A is 0, this means that the vector is called solenoid vector. This is just some remarks, okay? Next, curl. We call it curl, or sometimes I think we call it, I don't know, there's another name, I don't remember, okay? But a curl here, so a curl of a vector A, okay, vector, okay? So we have vector A, curl of a vector A is the cross product, okay, cross product. So we have the curl, okay, this one, we have this partial derivative, cross product of vector A. So how do we do this? We do, I hope you remember how to do the cross product, but for me, I write it this way. Maybe you have other different ways. For me, I usually write it, I prefer to write it like this. So, okay, X. Sometimes I just write it like this, Z. And then AX, AY, AZ. Okay, the cross product. I prefer to write it this way. So we want to calculate the cross product. So for the first component, okay, the component X. So we imagine, close it, the first one. So only Y, AZ minus We do like this, right? Cross product minus the AY Z, like that, right? Okay, and then the second one, the last one first, because the second one is a bit different. Last one, okay, Y X minus X Y, okay, 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 and the second one, yeah, I write it smaller, right? Wait. X, Y, Z, X, Y, Z, Z, Y minus Y, Z. Okay. Bawah dulu. Y minus AX Y. The middle one X. But it's okay, minus A Z. Okay. Okay, that is the rules for cross product. Okay. So
Doctor,
yeah.
sorry to interrupt, but Ash is waiting to join the video call.
Okay. Okay, I only receive application from Ilham. Okay. Apa tadi? Sekejap eh. This one. Okay, curl. Sekejap eh. Tengok nak buat tak. Okay, I already have example here. Okay. Okay, example curl of okay, cross product A. Okay. Okay, example of curl A. Okay. Okay. This is the vector f y power of 4 minus x, etc., etc., etc. Okay, in terms of I, direction I, j, and k. So determine curl A at point 1, 3, and negative 2. Okay. Okay, try to do that. Okay, we have an example here. Okay, because I want to go faster. Okay, so this one, the first one, okay, the derivative of the partial derivative of AZ, okay, AZ minus AY, AZ minus AY, okay, and then the second component, partial derivative of x of AZ minus the AX, okay? Either you do like this, you put minus outside, or I put like this, AS, AZ. So, okay. And then last one, x square plus y square. This one, AY minus this one, AX. Okay, AY minus AX. Okay, so make sure the position and plus minus, you put it correctly, okay? So the answer for all of this calculation, we have this x minus x squared z, okay, etc., etc. Okay, you can try this later on. Okay, so when we substitute the 0.13 and -2, we have the curl A 2i minus 8j minus 106k. Okay, so the curl A, we have initially a vector A, and the answer also is a vector, from vector to vector. Okay. Okay. So this one you can try later. Okay. So this just about the same as the example given just now. Okay. Next, so remarks vector A is a vector function and curl A is also a vector function. So properties of this operator. Okay, vector, we call it it's called vector differential operator. So it is defined this way: the partial derivative of x, y, and z in the different direction I, j, and k. Okay, so so that's it for differential. Next is vector integral. Okay, how do we integrate a vector? Okay, so vector integral, the concept of vector integral is the same as the integral of real value functions. The same as, the concept is the same as if you have a normal function, a scalar function. Okay, so example, the rules. Okay, so if we have a vector A, so the integral of a vector A, you have the same as a differential. You have to integrate each of the component of vector A, ax, ay, and z, and az separately. Okay. So for example here, if we have a vector f, okay, so how to calculate a vector f at 1 until 3? Okay, so this way, so we have to integrate separately the at the I, J, and K. Okay, so the answer is 42I minus 2J plus 80K after substituting the range between 1 until 3. Okay. Okay, next, line integral. Okay. Line integral, ordinary integral, a function of fx, okay, it is just like the same as normal function integral fx. Okay, so for the function integral, normally we integrate along the x-axis, right? Like this. If you have function fx, for example, like this, okay, function fx. So if we do integral of the function fx, means that we calculate the area fx from x, for example, x0 until x final. Okay, when we do integral of the function fx, means that we calculate the area. We integrate along the x-axis. Okay, the area along the x-axis, like this, right? That is for function fx. However, if we for line integral, the integration is along a curve. Okay, so I have like this graphic here. Okay, it's playing just now. Okay, so if we integrate a function f, okay, this function f is along a surface S. Okay, so you have a line, a curve like this. Okay, so when we do integration of a curve, it means that we calculate the area of all of this in purple or blue like this. Okay, this is just to show you what does it mean by this integral. Okay, so line integral is the integration along a curve. Okay, So means that we calculate all this area. Okay. One more time. So imagine you have a function f. Function f is along the surface. Okay. And you have a curve C, A to B. Okay. So when we said line integral, do the line integral means that we calculate the area, okay, of the curve like this. Because it is a surface, okay? It has a surface with 3 direction. Okay? So that is, what does it mean by line integral? So it's a bit different than the normal integral of a function that we have learned before. Okay? Okay, next is scalar field V integral. Okay, if there exists a scalar field, okay, V, scalar field V, along a curve C, then the line integral of V along C is defined by this way. Okay, so it is a dr is a vector. Okay, so for example, this is okay like this. The curve. How to explain? If there exists a scalar field V, okay, so you have the scalar field, this like this one, and then the line integral of V along a curve C is actually defined by this area. Okay. Okay, you have curve C, A to B. Okay, we want to integrate from A to B. Okay. Then okay. Okay, so means that we calculate the surface area all of this from A to B along the curve. Okay. Actually, the calculation is not too complicated. It's just that when we define, just to clearly define the in graphic, it looks like it is complicated, but the calculation is not complicated. Okay, we will see this one. Exercise 5. Let me see, exercise 5 or exercise 6? Okay, so VSY square. The grafik dia je nampak macam complicated, tapi calculation ni insyaAllah tak complicated sangat. Okay. XY square Z. Okay. We'll do this one, example. Okay, if we have the V, okay, the scalar field V, SY square Z, and a curve C is given by, so the curve is defined as X, Y, and Z. Okay, so X is 3U, Y is 2U square, and Z is U power of 3. Then find the integral, okay, the line integral of the scalar field V, okay, along the dr, along C, along the curve C, from A to B 0, 0, 0 to B 3 to 1. Okay, this way. We first have to, okay, we just rewrite. Okay, so we have V, V X Y square and Z. So X, what is X? We have to change the X, Y, and Z. So X is 3U. Y is 2U square, and then square again. 2U square, square, Y. And Z is U3. Okay, so V will become, just change V first. So V will become 12U power of 8. Okay, that is our V. Okay, and then next we define dr. Dr block. Okay, dr is a vector. So dr is in terms of x, y, and z. Okay, so first dx. So dx is 3 du. I write first the definition so that you understand better. So dr is dxi plus dyj plus dzk. Like this. Okay. So what is dx? Just now we have x equals to 3u, right? So dx is 3 du. Okay? So the same for dy and dz. Okay? Okay, dx is 3 du. Okay? So 3 du, 3 dui plus 4u du, 4u du j plus 3u square du k. Okay, direction k. So this is your dr. Okay, this is your v and this is your dr. Okay, next, the question given. Okay, you have point A and B. Okay, so again for point A and B also we need to change because the point A and B is given in terms of x, y, and z. So A 0, 0, 0. A 0, 0, 0. Okay, so x just now is 3u. So means that 3u is equals to 0. Okay, and y 2u square is equals to 0. And u power of 3 is also equals to 0. So from here, we get the point u is 0. Okay? In order to satisfy these three functions, 3u equals to 0, 2u square equals to 0, u3 equals to 0. So means that u is equals to 0. If we change the value, okay? So B3 to 1. Okay, 3 to 1, the same method. So we get u equals to 1. Okay, now that we have all these functions in terms of u, so we just combine it and integrate. Okay. So VDR just now, integration from point A to B, VDR. Okay, the answer for VDR just now. So this is B is u equals to 1 and this one u equals to 0. So V just now 12u power of 8. Okay, multiply with dr that you get just now 3u from I in the I direction, 4u du j plus last one is now 3u square duk. We look to du. I missed the du. Okay. Du k. Okay, this is dr. So dot product we just multiply, include. Okay. So and then we integrate separately in terms of I, j, and k. Plus. Huh? Okay, so 12u power of 8 multiplied with 3u, so we get 36u power of 9 du, etc., etc. So the answer, we by substituting the value 1 and 0 of u, so we get 4i plus 24/5, or you want to write in terms of this decimal also can, plus 36/11k. Okay, so that is the answer. Integration. Okay. So just a normal integration. Okay, it's just that we have to rewrite the function in terms of u, because the value is given u, and then just combine the dr, okay, dr, the vector dr, and multiply with vector v. Okay. So the same thing, try to do the same thing for exercise example 6. Okay, the same method. Okay, next, vector field. Okay, vector field, okay, vector field. Just now is it was a scalar field. Okay, this is vector field. Let a vector field fx, fy, fz, okay. The difference here is, okay, just now you have a scalar like this. The vector v, the vector v is a scalar like this, sy square z. Okay, this one, this is a vector. So you have component I, j, and k, and then you have to multiply with dr, the dot product. Okay, so the scalar product. Scalar product of vector f with vector dr. So we apply the rules of the scalar product, the dot product. Okay, just multiply, and when we get this, okay, I with component I and component I, j and j, k and k. Oh, shit, masuk. Okay, so if a vector field f is along the curve C, okay, vector field f is along the curve C, then the line integral of f along the curve C from a point A to another point B is given by this one. Okay, so means that we have to the same just now, we have to integrate separately, okay, the fx, fy, and fz. Okay, so can we do this one? Think dulu. Okay, we try to do this one. Ada answer problem. Okay, calculate the integral of vector f dot product with dr from A to B along the curve x, y, and z. Okay, the difference here is that f is a vector, just now v is a scalar. Okay, so the method is kind of the same, but we try to do at least one example. So we have to change first the vector f. F x square y at zj minus 2yzk. Okay, so you have vector f x square y direction I plus at z direction j, vector j, 2yz vector k. Okay, so just substitute the x, y, and z, okay, in terms of t just now, and then you get 32 t power of 4 I plus 40 power of 4 j and minus 40 power of 5 k. Okay, just substitute those x equals to 40, y equals to 2t square, right? Okay, for example, this one, this component x square, so you have 16t square, multiply again with 2t square, so you get 32, okay? And then the same for dr. Okay, dr is like just now. So dr, vector dr is a vector. So we have 4 dt. Okay, you have to derive the 40, x40. So you have 4 dt I plus 40 dt j plus 3t square dt k. Okay, so that is dr. Okay, so we just combine the scalar product like just now. Combine both f and dr. Okay, so fdr, scalar product fdr will become okay. So f and dr, okay, we like multiply, so we get 128. Okay, so the after we multiply the scalar product, we will have a scalar answers. Okay, function. For I with I, j and j. Okay, plus 16 t 5 minus 12 t 7. All of this dt. We just factorize the dt outside. Okay. And then, okay, the same as just now, we have to change the point A and B in terms of t. So the same method, we just have to compare. Okay, the x is 40 is equal to 0, 2t square, y is equal to 0, and t cube z is equal to 0. So t is equal to 0. Okay, and also for b, 4, 2, 1. So when we compare, we get t equals to, so for a, point A, we get t equals to 0, and point B, t equals to 1. Okay, so and then we integrate like just now. Okay, we have the range 0 to 1, and we have the function fdr. So we integrate, and the answer, we will get the answer. Okay. Okay. So the answer of integral b to a f dr is 2623 over 30, or you can change it into decimal. Okay. Okay, that is exercise 7 and exercise 8 also given here, and the answer is given here. You can try this by yourself. Okay. Exercise 8 is the same as exercise 7 just now. Next, double integral. Double integral. Double integral is the same, just like a surface. Okay, so you can try this one. The answer is 4 units. 4 unit square or 4 meters square. Okay. Given the function f xy, okay, in region R, bounded by a straight line x 0 and y equals to x, and y equals to n, and y equal to 2. Find the double integral dA in both order integrals. Okay, so you have to define the area, the function, okay, and then integrate in terms of x and y, and you get the answer 4. So we move on. Green's theorem in a plane. This is just a rules. Okay, if C is a closed curve in counterclockwise on plane XY and given two functions P and X. Okay, so you have this rule. Okay, the double integral. Okay, the surface double integral is actually the surface. Okay, the surface of this function is equals to the curve, the integral curve of this function. Okay, where S is the area of C. So to prove a Green theorem, okay. So imagine we have this function x square plus y square plus x plus 2y. Okay. So with the boundary value, boundary is defined as x0. So we only consider x at the line x0. Y equals to 0 and x square plus y square. So this is like a circle. Okay, with a radius 2. So if we write this, okay, this function, if we sketch this function, the function will become a curve like this. It is like a circle, but because due to the boundary, because the boundary for is x0 and y0, so we only consider this plane. Okay, we only consider this plane because x0, y0. Okay, so this function is actually a whole circle. But since the boundary is x0, y0, so we only sketch this plane. Okay, the first quarter, you see. The first quarter of the clockwise. Okay, so we don't have to do this, but okay, means that if we calculate the integral of this, okay, integral of this, and we can prove that the Green's theorem, okay. Okay, next, just surface integral. Okay, the surface integral, scalar field and V integral. Okay, if scalar field V exists on surface S, okay, surface integral V of S is defined by this way. So S, the area, the surface area, is actually a function like a dr just now. So we can write the function, the ds must have direction which is normal to the surface. This is very common in physics, electromagnetic. Okay. For example, you have a surface like this, okay? And then, okay, just a small ds, okay? Maybe you have a ds, a small surface pressure, and the n is the normal, okay, direction of the small surface, okay? So when we want to define ds, the vector ds, so vector ds is actually the product of the normal vector n, which is perpendicular to the surface ds. Okay, so if we have a surface ds, a small value, then n, the normal function is always perpendicular, orthogonal, okay, to the direction of the surface. Or n also can be defined this way, okay, differential of s over the magnitude of s. Okay, for example, okay, because we have done in the previous chapter about the heat flux. How to write? Okay, for example, okay. We have a rod here and the heat flux, okay, heat flux, the heat exchange is this way, okay, the heat exchange to the surface For example, this is ds, the surface. Okay, the surface at the wall or at a road. Okay, this is ds. Okay, small surface, small area. So the normal function will be exactly orthogonal or perpendicular to this to the wall or the road direction. Okay. Okay. And then example, scalar field V X Y Z defeated on the surface S, surface which is like the circle just now, between Z0 and Z3 in the first octant. Means that the plane. Okay, because you have X Y Z. Just now the example is only X Y, so X Y you only have like 4 plane. So macam ni. Okay, just now we only see example like this, right? Because we only define X and Y. So X, Y only have 1, 2, 3, 4. That's why we mentioned this now first quarter. Now, if we have X, Y, and Z, means that 2 power of 3. So we have 8. Z. So we have 8 planes. So this, but to solve this example, we only consider the first octant, means that the first plane. Okay, octant 8. Okay. So evaluate the integral surface of V ds. Okay, I have the solution here. So okay, V ds. Okay, of the surface S. Okay, given the surface S is like the function of a circle just now. So gradient S is this one. Okay. So we do the partial derivative of in terms of X and the partial derivative in terms of Y. So we have this scalar, this gradient of S is 2xi plus 2yj. And then, okay, the magnitude of this gradient S, okay, square root, etc., etc. So to find n, so we have this value, okay, n. Okay, gradient S over the magnitude of gradient S. Okay, now that we have n, so this is n, and then we copy back the V just now. V is xyz, okay, xyz ds. Okay, so just multiply all of this, so you get 1 over 2 x squared, etc., etc. Oh, dah habis dah. Okay, so just integrate this one like a normal integration. Okay. Okay. This is you can as example you can do this later on. If V is a scalar field, so we have V s y z square. So the same as the example just now. Just that here the region is x square plus y square equals to 9, means that the radius is 3. Just now the radius is 2. Okay, so between z0 until z2 in the first octant. So just integrate, okay? Like just now example, just combine the function, define the vector normal S, okay? The vector normal N, and then do the dot product, multiply, and you integrate like the normal integration. Okay, vector field, F integral, okay, just V is a scalar, F is a vector. So for vector, okay. Give me something that okay, we try to do this exercise 11. Okay, we try to do this exercise 11. Evaluate the integral of vector f ds. Okay, first, we try to sketch first the region. Okay, the region mentioned in the question, the surface, the boundary values, etc. Okay, so for this one, so imagine we have x, y, z. Okay, x, y, z. Okay. So surface S, which is defined by x squared, y squared plus z squared equals to 9. So since we have three axes, x, y, and z, means that this is actually a sphere. So susah sikit, okay. So it's like a sphere, okay. All of the three axes, x, y, z. Okay, with the radius 3. Okay, 3 power of 2 is 9. Okay, but this given surface of a sphere is bounded by x0, y0, and z0. So we only consider the first octant, the first plane. If you have x, y, z 3 axes, means that you have 8 plane. 8 plane. Sebab the boundary condition for this example is x, y, z 0. So we only consider the first plane, first octant. So so we forget about the other plane. Okay, we only consider one plane. So like this. So the sphere become this, only this. Okay, so radius 3, x3, y3, z3. So this is the 0. Okay, O. So this refer to a sphere with center 0, 0, 0, and radius r equals to 3. Okay, so like just now, we have to calculate the gradient S. Okay, the gradient S will become, okay, so do the derivation of each of the component. Just now, the component, jadi component yi2j plus k. Okay, so no, bukan. Derive the S. Okay, derive the S. So x square plus y square z square. So you have 2x I plus 2y j plus 2z k. Okay, x square y square, because s is x square y square z square. So we just get a derivation of each of the component. And then the magnitude S is 6. Okay. Because we substitute x, y, and z 3. X3, y3, z3. Okay. The magnitude, by substituting x, y, and 3, you do the square root. Okay. And then you get the answer 6. And then n, so n, your n, the normal, okay, the normal vector will be delta S, the gradient S, okay, over this. So you have the vector function to xi, to yj, to zk over 6. Or you can okay, to 1 over 3 to divide by 6. So xi plus yj and plus zk. This is n, the normal vector n. Okay, and then we combine all of this with the vector f. Okay, so pada ini.
Doctor,
What?
the modulus is, shouldn't it be root over of 2a square plus 2a square plus 2a square? That means, Doctor, root over of 12, right, Doctor?
The magnitude, the modulus.
Yes, Doctor. It is root over of 2a square plus 2a square plus 2a square, right, Doctor?
Okay, wait. We see. 2x. 2x square plus 2y square plus 2z square and square root, right?
Yes, Doctor.
Okay. Okay, so 2 pada so 4x square plus 4y square plus 4z square square root, and then just now 3 so 3 squares, 36 plus 36 plus 36 square root.
Doctor, x, y, and z are given, Doctor. The values of x, y, z. Aren't they given, Doctor, 0? X equals to 0, y equals to 0, and z equals to 0 as the boundary condition.
No, yeah, 36, 36 plus the, wait, 36 plus 3, 36, 72 plus 36,
Doctor, I mean that for the x value, y value, and z value, the boundary condition is given 0. So, Doctor, shouldn't we actually input 0 in the equation instead of 3?
No, the surface, okay, the surface just now that we sketched, okay, the surface is bounded between all the x, y, and 3 just now.
Yes, Doctor. I get it now, Doctor.
Why? Yes. Right.
I actually, Doctor, mixed it up with the boundary conditions because x equals to 0, y equals to 0, and z equals to 0. So sorry, Doctor.
Okay?
Okay, Doctor. Thank you so much, Doctor.
Okay. Okay. We integrate, okay? Integrate. So, integration of the surface f ds. Okay, so this is a vector, this is also a vector. So you have just now f y I plus 2j plus k. So multiply with the n that we have calculated, 1 over 3 sy. Okay. Then and ds, don't forget ds at the end. Okay. Okay, so we multiply of this. So you have 1 over 3 s x y, okay, the component for I, plus 2y, the component for j, plus z, the component for k, ds. Okay. Okay. Is it doesn't given the value point, so you just integrate this one, okay? Integrate into sy plus 2y plus z. Okay, saya tak tuliskan value. Okay, so we integrate this function for each x, y, and z from 0 to 3. Okay, because the center is 0 and the radius is 3. So it's like you do the triple integral. Okay, x, y, and z. Okay, and then next, I think this one given. Like this one, volume integral, scalar field VF integral. If V is a closed region and F is a scalar field in region V, volume integral F of V is F dV, okay? F dx dy dz. Scalar function, okay, example, exercise 12. Exercise 12, scalar function f equals to x defeated in one cubic that has been built by planes x0, x1, y0, y3, z0, z2. Evaluate the volume integral of f of the cubic. Okay, so okay, the menu, exercise 12. So you have f dv in the volume. Okay, so z from 0 to 2, y from 0 to 3, and x from 0 to 1, right? And the function f is 2x. 2x. So this is dx, dy, dz. Okay. So first, we do the integral in terms of x first. So you have 30. Okay, for x is x square over 2. Okay, 2 kat depan. Okay, x. And then, okay, the range for x is 0 till 1. Okay, and then, so we have, okay, this one, 1 over 2. Okay, and then this one, 1 over 2. Okay, just factorize the constant z. Okay, and y d z. Okay, because integration of dy is y. Imagine like we have y 1, so the integration of dy is y. Okay, so that's why we have y here. And then the same for z. Okay, 3 to 0. So we have 3 in here, 3 minus 0. Okay, here. Okay, cut out. So we have 3 dz from 2 to 0. So just integrate this and you get finally equals to 6. Okay. So that is a volume integral of the cubic just now. time is it? 3:21. Okay. Okay. Next example. Okay, this is explained. Okay. Evaluate vector f dv where v is a region bounded by x0, y0, z0 and 2x plus y plus z equals to 2, and also given the vector f is 2z plus y. So, okay, like the surface just now, ds, right? So here the volume, we have to first try to sketch the boundary condition. So for the first plane where x and y equals to 0, okay, for this function, okay, where the plane intersects with z axis. So if x, y equals to 0, then we have z equals to 2. So the same for the next plane, the plane where x and z equals to 0. At y axis, we have y equals to 2. And for plane y and z equals to 0, we have the x axis equals to 1. So we have all these points 0, 0, 2, 0, 2, 0, 1, 0, 0. So we have this this boundary condition. Okay, if we sketch the surface in this plane, so we have the line integral from x0 to x1, and then we have a surface integral from line y0 to line y0 here to line y equals to 1 minus x, because we replace the function here. And then last one is the surface where z equals to 0 to the surface of 2x plus y plus z equals to 2. Okay. This is how you define the integral function, the range. I repeat, okay? Okay. We have to evaluate the vector f in the region V, where the region is bounded by x0, y0, z0. Okay? And we also have this boundary condition. This is the boundary condition. This is not the function of f. The function of f is this one. Okay, so we have this boundary condition to x plus y plus z. Okay, so how do we determine the boundary? Okay, first we use the plane to x plus y plus z that we have. Okay, this function, this plane. So we have to define where does the plane intersects with the z axis, y axis, and x axis. Okay. So we get x equals to 1, y equals to 2, and z equals to 2. Here, 1, x equals to 1. So we know that this plane intersects with x at, cross the x-axis at point x, point 1, and intersects with y at point 2, and with z-axis at point 2 also. Okay, so that's how we get this plane. Okay, this plane, the function for this plane is 2x plus y plus z equals to 2. Okay, that's how we sketch, we achieve to sketch this plane. Okay, by substituting this x, y, 0, etc. in the plane function. Okay, and then so the surface just now, so when we sketch the plane, we see that for x, okay, the boundary for x is from 0 until 1. So we have to do the integral later on, okay, for x from 0 to 1. But for y, okay, the integration is from 0 until this line, where this line is 2, 1 minus x. Okay, because z equals to 0, z equals to 0, this plane z equals to 0, so we have y equals to 2, 1 minus x. And for z, it is from z 0 until this plane. Okay, where the plane is 2x plus y plus z. So use this one. And we have 1 minus x minus y. Okay. So to calculate the integral of vector f over the volume V just now. So we have this. Okay, the vector f dz dy dx. So we solve the z first because in the function z we have x and y. So we start with the z first. Okay. So this is the function f, the vector f. Okay, and then we have to do integral z from 0 until to the range from 0 until to 1 minus x minus y. Okay, and then calculate and substitute this value, and then we have we left with x and y, and the same thing we do the integral from 0 until to 1 minus x until we only left with the value x. And we substitute the value x from 0 to 1, and finally we get the answers for the vector integral of f is 2 over 3 I plus 1 over 3 k. Okay, just that you have to we have to sketch first the boundary, so from there we can see what is the range of the integral. Okay, this one, exercise 13. I think it's the same as the example just now. Wait, Same. I just give you the answer for exercise 13. So you can try to do the same as exercise 12 just now. So for 13, the answer is 18 pi. Or you can translate the pi, 2i plus j. Okay. So the same as example just now. Okay, next is I think sikit ya. Okay, nak beda. Okay. The last few slides is actually a theorem, like the Green's theorem just now. So there is another two theorems for vector calculus integral. So what this Gauss divergence theorem said, it says that if S is a closed surface including region V in vector field F, so we have this definition is that divergent of the vector F over the region V volume, which is a volume, equals to the integral of vector F with in the surface ds. Okay, so this is a theorem, a rule. Okay, so it means that if you do divergence here, this divergence will equals to this value. Okay, just example, some explanation bit. Prove Gauss theorem for vector fields. We just want to prove whether the theorem is correct or not. So just calculate the left hand side and the right hand side, and then prove that the answers are the same. So example, we have vector f in the region bounded by planes z0, z4, x0, y4, and x squared plus y squared equals to 4 in the first octant. So the same you have to try to sketch. So if we sketch the boundary, we get this solution. Okay. Z0 until Z4, X0, Y0. Z0 until Z4, X0, Y0. Okay, and then we have this function. This function is like a circle just now with a radius 2, XY. So that's why we have this plane. This circle, like a circle here with radius 2 because of this function. Okay. So we get this surface. Okay, so we have to integrate this surface. Okay, so for this problem, the region of integration is bounded by 5 planes. So we have 5 planes. The first plane S1 is Z0, S2 Z4. Okay, S1. Okay, where S1? So S1 is Z0, this one. S2 is Z equals to 4, this plane. S3 is Y equals to 0. S4 is X equals to 0. And S5 is this curve, this circle. Okay, X squared plus Y squared equals to 4. Okay, so to prove Gauss theorem just now, we evaluate both the left hand side and the right hand side, the divergence and F. So the calculation is the same method as the previously. Okay, the answer should be the same. Okay, and then last one is the Stokes theorem. Okay, so what is Stokes theorem said? Stokes theorem says that if a vector F is a vector field on an open surface S and boundary of surface S is a closed curve C, therefore, okay, we have this theorem which said that a curl F, okay, remember curl F is the cross product of F over ds, surface S, is equals to the dot product of F and along the curve C. Okay, so that is what Stokes theorem said. Okay, so example here, we have a part of the cylinder is X square plus Y square equals to 9. So this is like a circle with radius 3 between Z0 until Z4 for Y positive above 0. A half of the circle with radius 3 at Z equals to 4 and plane Y0. These are all the boundaries. So prove the function vector F. This one, prove that the Stokes theorem for this case. Okay. Okay, so we have the boundary here. Okay, we can divide the surface S into 3 different surface, S1, S2, S3. So first one, S1, X square plus Y square equals to 9. So it's the circle which is valid for Z0 until 4. So this curve, this circle is for Z0 until 4 and with Y positive, so only this part, Y positive, okay, only the right hand side part. Okay, and then S2 is this one, which is Z equals to 4, half of the circle with radius 3, and S3 is Y0, okay. We can also mark the piece of curve C as C1 perimeter of a half circle with radius 3, straight line from minus 3. Okay, because we have to prove Stokes theorem, we have to do the integral of the surface at one part, and the other part we have to do the integral of a curve. Okay, so one is how do we define the curve? Okay, the right hand side part. Okay, we can define the curve which is C1 is the perimeter of a half circle with radius 3. So imagine half circle. So this is like the half circle, the curve C1. The C1 here, the curve C1. Okay, and another one, the curve straight line from negative 300 to 300. So C2 negative 3, negative 3, negative 300 to 300 here. Okay, so that is the surface, the curve C2. Okay, let's say we choose to evaluate the curl F first. So we calculate the curl F over the ds defined just now, S1, S2, S3 just now. S1, S2, S3. Okay, okay. So actually the Stokes theorem and Green's theorem, Gauss theorem, it's just to it's the application of those vector integral calculus that we learned just now. Okay, so we learn first the definition, the calculus, how to calculate the vector value, the integral of a scalar field, the integral of a vector field, and then the integral of those scalar and vector in a curve, in a surface, in a region. Okay. So and then lastly, we have this theorem which prove that this divergence is equals to the dot product, etc., etc. Okay. So just to summarize, the slides, my slides are finished, but just to summarize what we have learned today, so that you hope you understand better. Okay, I just want to summarize what we have seen today. So those exercise and example, I hope you try to do by yourself, okay? Try to calculate, because actually calculus, it doesn't involve like the numerical that the previous chapter, those previous chapter from chapter 1 to chapter 4 that we have learned earlier. It is more involves the programming, etc., right? But calculus is more on the calculation, so you just have to understand the method, the steps, and then just know how to position, okay, just to substitute all those values. Okay, just to summarize what we have learned today, we have learned first the definition of a vector, derivative. Also, this one is okay. Okay, gradient. We have learned about gradient, gradient phi or gradient of a scalar function. So what we say, what we know about gradient is the from a scalar to a vector, right? So we can write it as like this. Okay, same definition gradient. Okay, second one, we have learned about the divergence. Now, we have seen divergence. So divergence of a vector A, divergence vector. Okay, or we can also write it this way. So divergence, we must add this dot product. Okay, so divergence of a vector A is from a vector to a scalar. Okay, and then curl. Curl is the cross product of a vector. So we can write it like this, cross product of a vector. So from vector to a vector. Okay. And then those of these are the vector differential, okay, derivative calculus. Next, the next part, it involves integral. Okay, so what we have learned in for the integral, line integral. Line integral over a curve, okay, curve C, and then we have the scalar field integral also over a curve. Okay. Scalar, okay, scalar integral V, and then we have seen vector integral F, and then double integral of a function, Green's theorem. So what Green's theorem says, so there are three theorems, Green's theorem, Gauss and Stokes, Green's theorem, and then okay, surface integral of a scalar, scalar field, surface integral. Scalar. Okay. Surface. No, I want to write scalar field. Scalar V integral over a surface. So like this. Okay, V ds. Okay. So now, at first we have scalar integral V and vector integral F over a curve. So this is over a surface. So for a surface, we have to define the normal vector. And then we vector field for vector F integral. So vector F integral. Vector F integral. Still over a surface. And then volume integral. Scalar field F integral. Oh, specific. Okay. Okay. Scalar. Okay, but this time we use a notation F for scalar F because we don't want to get to be confused with the volume V. Okay, so F. So this F is a scalar, not a vector. Okay, so scalar F integral, but over the volume. Okay, so we write F dV. Okay, volume. And then the vector field integral. Vector. So this time this is a vector. Vector F integral. So vector F over dV. Okay. And then the theorem, Gauss theorem, and the application, Gauss theorem, and Stokes theorem. Okay, so I think that's it. Okay, so I just summarize because I don't want so that you maybe understand better. Okay, so you have line integral for integral. You have line integral first, and that's how to integrate scalar over a curve, and then how to integrate a vector over a curve. So this one is for curve. This one is for surface. And the last one was for volume. Okay, so scalar vector, scalar vector, scalar vector, curve, surface, and volume. Okay. So okay. So that's all for calculus. Okay, so actually we have finished all the chapters. Okay, so I advise you to try all the example exercise in these slides. Okay, just so that you familiarize with the calculation of the differential derivation and integral. Okay. And then you have one last assignment, but the assignment is about the partial derivative. Okay, wait, I'll share the slides. So last assignment. Okay, so last assignment, assignment number 4. Ini. I think this one, yes. Okay. 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 So assignment number 4 is about a heat equation, parabolic. Okay, remember previous chapter about the PDE, partial differential equation. We learn about elliptic and parabolic. Okay, what is the difference of those two? Elliptic is more on a steady equation. Okay, means steady means that it doesn't change in terms of time, or we assume that it constant in terms of time, doesn't depend on time. But for parabolic, it unsteady equation, means it is dynamic and depends on time. Okay, here. Okay, so we have the parabolic equation for heat equation. Okay, heat transfer. So we have to solve this PDE, partial differential equation of heat. So we have the partial derivative, the second order of u over x minus the partial derivative of u over t. So these are the condition, the boundary condition for u at u 0 t, 0 for x, and means for throughout the period t. Okay, at the initial point 0. Okay, u equals to 1 at point t, means u0, x0 and x1 at point at those extreme points left and right at any times is equals to 0. Okay, another boundary condition, which is u at all distance, but at the initial starting point t0 is equals to sinus pi x. Okay, so those are the boundary condition for u. So use the step size h 0.25 given here, and k, this is a parameter like a thermal conductivity for the heat equation. So we define k is 0.25. To find the function u in terms of function of s and t for boundary x 0 to 1 and t also 0 to 1. So means that if the step size is 0.25 given here, so means that we have u1, u2, u3 until u4, okay, to achieve the final point t equals to 1. Okay, for example, t is equals to 1 second, so we have you have to calculate u1 at t u0 first, u0 at t0, u1 at t 0.25, u2 at t 0.5, and then etc. And for those time, for each time, there is different x, right? So don't forget about x. So you have x1, x2 until x until 0, 1. Okay. Okay. Okay, the same instructions, just this one, number 2 is different. Okay, use explicit method to solve the problem, then repeat again by using the implicit method. So you have to try to solve with the two methods, explicit and implicit, given in the slides previous in the chapter 4, and the rest are the same. So I give 2 weeks, okay, until week 14, or by the end of week 14 also can. Okay, so by the end of June to finish the assignment. Okay, so I hope that not too complicated. Okay, just try to solve this heat equation given step size h with this value, boundary value. Okay. Okay, so already 3:51. So lastly, attendance. Wait, okay, I'll stop recording first. Stop recording. Oh my God.